So this footing here supports the column that you have just designed in your submittal file. So this load here needs to be supported by the soil. And if you just put the column here without any footings, this column is just going to be penetrating the soil because the soil is going to be very soft, doesn't have that much of a resistance. So you need to put here a pad or a footing. So this column load that you designed, you can see here P dead load, right? And P life load. And based on that, you're able to find out P ultimate. You remember P ultimate that you designed the column for? So same information that you have done in the previous submittal, you're going to be using here in this submittal. So loads is going to be the same. Why? Because this column needs to have a pad to support this load. So the same load that goes to the column here that you designed the column for at this section, right, is going to be the same load that get transferred to the footing eventually. Any questions about the load on the footing? I'd like to hear from you before I proceed. Yes? Are we clear on that? 100%? The load that you design your column for is going to be the same load that you're going to be designing your footing for.
So Professor, can I clarify really quickly?
Sure.
So you told us for the submittal 5 that we find the P ultimate for the roof and the floor, and then you would do the P ultimate of the roof plus 3 of the floors, and then that gives us our ultimate for the column, right?
This is correct. Imagine that here is the roof level, right? And then you have 3 more levels. Don't worry about the spacing or the scale. See, here's 3 floors and the roof. And then you added all the load. So the load that you have added up is actually going to be the load at this point, right? Which is going to be the same load that the footing supports. So the design load for the footing is going to be the same as the design load for the column. Because what else is going to be taking the load from the column, right? It needs first to go to the footing and then after that to the soil. So in the first item here, I'm saying based on the column submittal, use the largest column load. Yeah, you remember we have taken the largest internal column load. So this is going to be the same one that you have used to design the largest footing only. So you're going to be doing only one footing design. And now after this, it says use the allowable soil bearing pressure. Now I don't know what's this about. This is what we need to cover today. So please stay focused with me because I want to cover this submittal. So you don't really have to spend lots of time working on it. It's so simple and easy. You can do it quick. And then it says you design the bottom reinforcement of the footing and then check the one-way shear. So we need to figure out all of this item, the 3 items in today's lecture. Any questions on the column load again before I proceed? You're good? Right, excellent, good. Now let's move to the footing with the foundation. Slide set. All right. What we're going to be working on is going to be called gravity pads. This is going to be for today's lecture. And this is what we're going to be covering in this course. But you know that gravity means dead load, life load, and any weight of any equipment or maybe weight of snow or whatever. And non-gravity is going to be, let's say, for seismic, which means to resist earthquake forces. I'm not going to be working in here. I'm just going to be working on this, on the gravity. This is what I care about. And the one that you're designing here for your submittal is going to be actually for the gravity, for dead load and life load only. If you recall here, the load that you have in your column design was only dead load and life load, no other loads. So here in this slide slit, most likely I'm going to be working with gravity foundation. And in your submittal, it's going to be only about gravity foundation. Here's a system like the structure system. This is not a new slide. I'm sure that you remember this slide. So you have the floor system, second floor, or first floor, second floor, maybe third, maybe roof. And then you have all the total load coming from here, right, from the top. And then you have some load coming from the second floor, heads up, and then it goes down here, right above the first floor. Now new load is going to be coming from the first floor to this column. And then after that, the total load is going to be right here. So actually, this is going to be the total load that you just calculated out in the previous submittal. And as you see here, supported by a footing that we call here split footing. Or sometimes it's called isolated footing. What does it mean by isolated footing? It means it does not combine more than one column. You see here, here's one footing with one column, another footing, support another column. Sometimes the columns are very close to each other, so we do combined footing. We're going to be taking one example in that. But for now, what I care about is going to be this split footing or isolated footing. And this is exactly what you're going to be doing in your submittal for this coming Monday. So great. Same thing. See, even if you have a round column, like a spiral column, it's going to be supporting the roof, maybe one level, and then the load is going to be coming all the way. Total load is going to be coming to the footing. So the footing design load is going to be the same as the column design load. Another picture here shows you a section through a building. Sometimes we have a basement. And in this case, you have the load coming from here, right, going all the way down. And you don't just add the load coming from the roof and the top levels, because once you go down here, you need to add the basement load coming from the first floor, or the ground floor, if you like to call it this way. So this needs here to be into consideration. You don't ignore this. You don't say, here, I didn't take any basement, because actually you don't have a basement here. So the ground floor here does not dump any load on this column. But here the ground floor is dumping load on the column because it is a structural elevated slab that's supported by this column. Eventually it goes to the footing. Look here at the footing. It is not isolated, just isolated, because if you look here, you have other footings, you have other foundation. And you see here, it looks like a network. So you cannot call this to be isolated footing. So here's the load, and here's the load path. You may have a point load, maybe sometimes you have a line load. It depends on the equipment or the load source. And then you have some uniform load, like the occupancy load. Load goes from the slab to beams to columns, eventually to foundation. And guess what's going to happen after the foundation? It goes to the soil. So here I may consider it to be a point load. You know, when it comes to the column load, we call it to be a point load. It was in terms of kips. But once it goes to the soil here, it cannot be concentrated. So it needs to be distributed. So when you look here through the footing, if you look here a section through the footing, you're going to see here that the ground and the soil is responding with soil pressure. So you have applied soil pressure from the top, and then you have a reaction as a soil pressure. This contact pressure coming from the top is going to be the same as the pressure coming from the bottom. They need to be equal to each other. Because if the pressure coming from the top here is going to be higher than the pressure coming from the underside of it, of the footing, the entire footing here is going to be going through the soil. It's going to be failing. Now, the soil here and the concrete, any material, it has an allowable value, the maximum value that can support without collapses. Concrete, we do a check on the column design, and we have done this before. If you guys remember, we have done the column design. We said, here's the capacity of the column in terms of kips, and here's the demand, and we need to be sure that we have capacity more than demand. That was on the ultimate level, meaning P sub U. If you guys recall P sub U, we say 1.2 dead plus 1.6 live. We call this P ultimate. Same thing to the soil. This soil, it has a limit. And the limit is not going to be a point load. The limit is going to be like uniform load. Meaning, when I have a load here coming down, I can say, let's say P total load, let's say equals to 100 kips. See, this is good, okay? And let's say this footing is 5 feet by 5 feet. So we can say, okay. You can see the footing size, I'm going to say 5 feet by 5 feet. How much is the pressure below the footing? Now, you have a vertical force of 100, and the footing size is going to be 5 feet by 5 feet. Therefore, the area of the footing equals, I'm going to say 25 square feet, right? Good. How about the pressure below the footing? See the pressure, I can use here the term Q is going to be equal to 100. What is the 100 coming from? I'm going to say the 100 kips divided by 25 is going to be equal to 4 kip per square foot, KSF. So the pressure now in the soil, which means the contact pressure between the footing and the soil equals 4,000 pounds per square foot, or 4 KSF. The big question is, would the soil be able to support this soil pressure coming to it? Meaning, I have an allowable soil pressure, and I need to be sure that the applied soil pressure, which is 4 KSF in this case, is going to be lower than that allowed by the soil. So, okay, makes sense. I need to be sure of that. Now, once you apply the load in the footing, what's going to happen? You have some column reinforcing, you have some ties. Load is going to be coming like in the vertical direction like this, and here's a pad. Look what happened, if I may go here to the next slide. When you apply the vertical load on the footing, now we have this uniform pressure below the footing, and this uniform pressure is going to be forcing the footing to bend up a little bit like this. Therefore, if I'd like to come here and say compression and tension, tension is going to be at the bottom of the beam or the footing, and compression is going to be in the top. Therefore, the main reinforcing I need to add here is going to be at the bottom of the footing. Any questions about location of reinforcing? Give me a second. Any questions on the reinforcing location? Why do I need to have reinforcing at the bottom of the footing? You say, okay, here's the reason. You apply here the vertical load, and on the soil, you're going to have this pressure. And as I said before, this pressure, if I'd like to put it here, I'm going to say, let's say P equals 100 kips, right? And the footing size, I'm going to say 5 feet by 5 feet equals 25 square feet. Therefore, Q, which is the pressure, equals 100 divided by 25 is going to be equal to 4 KSF. So the pressure down below here is going to be equal to 4 KSF. And it's going to be pushing the footing up. So it's going to be bending this up like this. So actually the tension is going to be at the bottom of the footing. And look at some cracks. Just to illustrate here, tension is going to be at the bottom. And compression is going to be in the top of this footing. So I'm going to say this is going to be here compression. And then here we're going to have some tension. And I need to design this reinforcing for that. So actually when I do footing design, I have two issues. Number one, be sure that you're not going beyond the allowable soil pressure. And number two, I need to design for this reinforcing, like any concrete member. So first, you size the footing so that this pressure here is going to be lower than the allowed. This is going to be kind of soil design. This is not concrete design, right? This is not what we're learning here in this course. We're learning how to do concrete design, right? For members, for concrete members. But it's something that you need to do. It's going to be part of what you design here. You need to come up with the footing size, like length by width. Now, depth of the footing and reinforcing is going to be purely concrete design. Yes, okay, let's look here at the reinforcing. Here's the reinforcing for the column, and some reinforcing in the footing is going to be in both directions. Why? Because when this happens and one side of this footing is going to be going up or deflecting up, actually it's going to happen in both ways. If I cut a section here this way, or I cut a section this way, can end up with the same deformed shape that you're looking here at. Therefore, I need reinforcing in both directions. Any questions on that? Why do I need reinforcing in both directions? Why do I need the bottom, not on the top? You can say, look at this, or look at this. When you have the pressure coming from the underside of the footing, pushing it up, this is going to be bending up. Tension is going to be at the bottom, compression top. And this is true on both sides. It's going to be true on this side, and it's going to be true on this side, that side, and all sides. This is actually an actual picture of a plan from a project. And you see here that was taken at the site, at the construction site. And this is one of the projects that I was working on. And as you see here, you see it says here footing schedule, right? And you see here's the plan and shows the footings. And the contractor started to market different colors because he decided to cast this at one time, and other footings, which is giving black, he decided to do them another time. So this pink ones, they were supposed to be cast when I went there for structural observation. As you see here, it says C1 and then F10. What is C1? I'm going to say C1 is going to be the mark or the model for column 1. So this is going to be C1. This is going to be F10. Usually when we call it F10, it means that the footing size is going to be 10 feet by 10 feet. And you can see it here. Look at this. F10 is what? 10 feet by 10 feet. And look at the thickness, 24 inch. And it has some reinforcing in both directions. Line number 7 at the bottom. If you look here, it says bottom reinforcing, line number 7, line number 7. And in the top, usually we put some light reinforcing. It's giving only 4 rebars in 10 feet. Just imagine you have here 10 feet. I just put some light rebars. So these rebars are doing nothing, but they're going to be helpful to support other rebars that we have in the slab above it. But this is going to be the main rebars. Line number 7 in each direction. You see this? It's going to be bottom reinforcing, and here's the footing size. When it comes to the column size, look at this. It says here column 1, right? Here's column 1. Column 1 is going to be what? 12 by 16. And here's the reinforcing, number 6. And look at the ties. Number 4 at 6 inch on center, right? So now you have seen an actual drawing for some foundation. Okay. Here's the footing. As you see here, there is no formwork. They dig a hole in the ground, and they made it a little bit larger. And usually we ask for at least 3-inch cover. Look at this. They call this dobies, like this concrete pieces, the blocks. And they make this footing here larger by the needed size by at least, like, instead of the cover to be 3 inches, they make it like 6 inches. Just want to be sure. They don't want me to come and say, this is not enough cover. So they give me more cover than I need. So actually this footing, if it's supposed to be 10 by 10, they build it like 10.5 by 10.5 feet. So I'm okay with that. I mean, they put bigger footing a little bit. I'm okay with that. And look at the reinforcing. You have 9 bars here, 9 bars there. And they're supposed to put, let's say, for number 5, they just put, look, like 6 number 5. So I'm okay, yeah, put more reinforcing. This is an actual construction. This is here a wall footing. You see here it's kind of continuous, a very long footing, and the walls going to be built on the top of it. So when I went there, that was an early stage. They start just to put the reinforcing down there, and they looked at some of them, give them some comments, and then they continued and they were working on it. Now they cast the concrete. You see here's the footing is done, and the column is sticking up out. So look at this. Look at this, the column here, we call this some downs, right? And then they come here, they put this dowels, they're still sticking up, and now they start to put the reinforcing for the column. And here's the footing. You see that? They filled the hole with concrete. Same thing here, same thing there. And construction is just moving on. Now they cast the column. Now we're gonna have here a concrete slab, elevated concrete slab that they're gonna build together. So just to give an idea that the column load here, whatever column load that I'm gonna be designing this column for, this is gonna be the same load that this foot is gonna be supporting. This is here a picture for some wall footing. And you see here what happened? You're gonna see all the dowels, right? Just sticking up. And look at the footing, even when you look at the amount of concrete, they give you a little bit more concrete. Even the depth of the footing is usually larger than what I specify in my drawings. If I called it here 24-inch footing, I'm sure there's gonna be maybe 25 or 26, which I'm okay with. They make it a little bit thicker. This is not the case in beams and columns. In beams and columns, they are gonna be exposed, and you cannot play with the column size. You cannot make this column to be, let's say, larger than the size I put in my drawings. You cannot do it this way because for architectural reasons. Same thing for the elevated slab. You cannot make it higher or lower because you have a given building height that you need to maintain. But in foundation, everything here is going to be covered with soil, right? So it's okay to make it a little bit larger. Another big footing is going to be, actually, this is a giant footing. And this is for a flare foundation. If you look here, you see some anchor bolts, heavy anchor bolts. And this footing was about 21 feet by 21 feet. So it is really good size footing. Just one big footing, one giant footing. It supports this structure here. That was done in a landfill. Sunshine is up north, Santa Clarita. The height of this flare of this steel, I'm gonna say cylinder, big steel cylinder, is about 54 feet. Just, you know, it's made out of steel. And the weight is about 50,000 pounds. And they use it to burn the methane gas. So it's really heavy. And just imagine when you have a windy day, what type of movements, or you have an earthquake. That's why this footing is really large to support this. Now, in a case like this, I'm gonna say the loads on this footing, I'm gonna have here a vertical load coming from the weight of that thing, right? Plus, I'm gonna have maybe some earthquake forces gonna be acting like this, or maybe some wind loads. So the gravity footing that we have discussed that supports only dead load and live load is going to be exposed to only vertical load. But a footing like this is going to be exposed to a vertical load and some moment, and the moment is going to be acting in this way. So when the wind blows in this direction, this footing is going to be supporting some moment here. So actually this footing here supports gravity load and some moment coming from the seismic, which means earthquake force, is going to be or wind force. And if the wind is going to change its direction, it can be designed for a force in this direction or a force in this direction, or maybe a force coming in this direction, or it's going to be coming in this direction, like in X or Y direction, right? Because the earthquake force, it can hit in any direction. I cannot really control it. So we have here the actual soil pressure, which is based on the load demand. And then we have the allowable soil pressure. You see, what is allowable soil pressure? Allowable soil pressure, we have soils report or geotechnical report coming from geotechnical engineer. He is also a civil engineer working in the soil business. For us, we are structural engineers. And he will develop a report based on soil testing in the lab. He's going to say your allowable soil pressure is going to be this much. This allowable soil pressure, we also call it bearing capacity. Look at this, like this bearing capacity, which is the same as this. Q allowable, which means BC, allowable bearing capacity or soil pressure. So number one, I have here a vertical load, which means dead load and live load. And I need to figure out the minimum area required of the footing, like as a width by length, right? Otherwise, the allowed soil pressure is going to get exceeded. So I need to control here the demand soil pressure. Now, first, I need to understand what does it mean by P service demand. You say, let me give you this quick example. I'm gonna say, I have given dead load of, let's say, 100 kips. Life load, 40 kips. I have two demands, just so you know. In the past, we used to say P ultimate equals, if you remember this, 1.4 dead load, meaning what? Someone help me? How much is that? Are you guys awake?
1400.
1.4 times 100 is going to be how much? 140 kips.
140.
140.
I'm going to say I have another equation. It says 1.2 times 100 plus 1.6 times 40. And now I need help in this.
I got 184.
184 kips. Great. Do we call this to be ultimate load, or what do you call this? Yeah, this is why it is P sub U, ultimate. So it is not service. So the one I designed the column for was actually P ultimate. So when you do concrete design, you do ultimate design, all right? Which means factor loads. When you do foundation size, look at this. For foundation size only. You guys remember this? Very common mistake that people will be confused between service and ultimate. You say, I'm gonna say P service equals, remember this, just dead load plus life load. No load factors, meaning it's gonna be equal to 100 plus 40 equals 140 kips. It has nothing to do with this 1.4 times dead load, am I correct? It is not related to it. This 1.4 times dead load, this is the load factor, it's gonna be ultimate load that you need to use to design the concrete. To size the footing, you're gonna be using here the service demand, which is just dead load plus life load. Later on, to design the reinforcing in the footing, you're gonna be using this 184. So you have your ultimate demand and service demand. So I'm gonna be adding a note here. I'm gonna say this force, I'm gonna call this what? I'm gonna call it ultimate demand. Used for what? Design of concrete. Members. Like reinforcing. And this is what we have done in the past, you know, this is ultimate here. So I'm gonna say, how about this one here? What is the service? I'm gonna say this service load is used to do what? Design of foundation. I'm gonna redo this again. Size only. Are we good? Now we know the difference between service demand and ultimate demand. Service demand, which means just dead load plus life load, it is used to size the footing. Ultimate demand, this is when you include the load factors. You're going to be using it to design the reinforcing in the footing. So for the same footing, I'm going to have two different demands. One's going to be called service, because actually you're going to be designing the soil for, and the other one is going to be called ultimate, to design the reinforcing in the footing. This is usually a point of confusion. Lots of people is going to be confused and say, should I use the ultimate to design the footing size, or going to say no, it's just going to be dead load and life load? I hope it's clear, because I know that some people is going to be asking this question later. So, okay, I guess this can be the only new equation that you need to learn about, right? This can be the only new equation when it comes to foundation. The rest of the work is going to be stuff that you're exposed already to. It's going to be very similar to beam design, rectangular beam design. So, okay, let's see this example. It says the column dead load is 850. So this is going to be dead load, right? So let me write this next to it. I'm going to say dead load is going to be this number. And life load says 560. This is going to be life. We're going to be working with a square footing, square spread footing, proposed to support this column. Soil bearing capacity is 7,000 PSF. What do you call this? I'm going to say you can call this Q allowable, which means allowable soil pressure. Sometimes you call BC, bearing capacity, right? It says here, the most economical size of the proposed footing is. It says here square footing. Would you go by 12 by 17? Is this going to be a good answer? No, it's not square footing. 13 by 16 is not square footing. So actually I have two sizes to work with, 15 by 15 or 18 by 18. I said, okay, so what do I need to do this task? I'm going to go back here one slide and look at the equation. It says here the area required, this is going to be the area of the footing needed, the contact area, which means length times width. It's going to be equal to P service load divided by bearing capacity, allowable soil pressure. Allowable soil pressure is given. I have this. How about the service load? Do you have the service load, service demand? You say, well, here's the service demand. Quick example. Yeah, let me look. Service demand, just adding dead load to life load. So I can do the same. Just add these two loads to each other, right? Divide by 7,000. It's going to give me the needed area, and then compare it with the given area. So it's going to be the area provided, and this is going to be, if you take here P service divided by this 7,000, it's going to give you the area needed. So, okay, let me look at the example. Here's the P service demand. What is this? 850. I'm going to say this 850 is dead load is given. What is the 560? I can say life load is given. Total of 1410. How much area needed, contact area between the footing and between the soil? I'm going to say is going to be 1410 divided by 7 KSF. So I'm going to say this is the one which is 7,000 PSF. Or you can call it 7 KSF, which is the same as 7 KSF. So, okay, good. So the area of contact between the footing and the soil needed is going to be 201.43. Do square root of that. You need, because it's going to be square footing, you need a footing of 14.2. I guess the closest one is going to be 15 by 15. I wouldn't go to 18 by 18, otherwise it's going to be just too large, right? So I'm going to save by 15 by 15. You can say, well, for 15 by 15, I'm providing here 225 square feet, and I need only 201, so I provided enough. So this is good. I like this solution. So 15 by 15 is going to be okay. Any questions? So I guess you know how to size the footing in your project. You have dead load, you have life load, add them together, divided by the allowable soil pressure. Where'd you get the allowable soil pressure for this project?
It's on the criteria.
How much is it?
I believe it's 3,000 PSF.
Okay, let me quick go there. Do you see it now? In the red box, the soil bearing capacity is 3,000 PSF. Great, now I have it. So I guess I should be able to do this in this easy step. All right. Sometimes we have footings, and these footings, they support vertical load and moment. Like the flare, like other applications, from time to time you may have a vertical load and a moment. I said, okay, great. What should I do next? I said, if you have a footing here and this footing exposed to vertical load and also to a moment is going to be like this, I can come here and solve for the stress below the footing once for the vertical force for P and once for M. This is going to be the moment. and then add the effect of both of this vertical load and this moment with this equation that you guys have seen before. In mechanics of material, you have taken this combined stress, right? When you have vertical load and moment acting on a surface. So you say P over A, which is the effect of the vertical load. M over S section modulus, right? You guys have seen this before in this course. And then you say plus or minus. I'll tell you the reason for this plus or minus. Plus or minus, because in one side you're going to be putting compression here, and the other side you put tension. So at one point, the pressure is going to be additive, at the other point, it's going to be subtractive. Let me show you this. Here's the two sources. I have a point load P, vertical load, and then I have moment acting on the footing. The truth is, I have them happening at the same time. So what I'm trying to do here, I'm trying to split both of these two effects and find out the pressure due to the vertical load and the pressure due to moment, and then add them to each other. So I'm going to say here, the pressure due to the vertical load is going to be equal to P over A, which is F sub P, which is this one here. F sub P and then F sub M. F sub P is going to be the stress due to vertical load. F sub M, the stress due to the applied moment. So, okay, here's F sub P, P over A. Here's F sub M. It's going to be M over S. So here's going to be all compression. Just P over A. And this side, one side is going to be compression, one side is going to be tension. Now the question is, can the soil or the contact between the soil and the footing, can it be in tension, in true tension? You see, no, it cannot be in tension. Just imagine here that I bring this cup and then I put it here on my hand, right? Can I start to pull it up? Any resistance beside the weight of the cup? No. Same thing with the soil and the footing. Soil is not going to be pulling the footing down. So soil cannot take tension. Concrete has some tensile strength, but it's going to be very limited. Steel has very strong strength when it comes to what? To tensile. But in this case here, if the amount of tension on the soil is going to be just too large, just the footing is going to be lifting up. It does not provide any resistance to this tension on the footing. So I have here two cases. If the amount of stress, because look at this, this stress here is going to be added to this stress here. So the right side to the right side, the effect coming from the axial load, the effect comes from the moment. So the stress on the right side here is going to be Fm plus Fp. Why is going to be additive? Because this is here compression, and this here is going to be compression. But when it goes to the left side of the footing, which means this side, and which is the same as this side, don't forget that both of these two loads you have at the same time. You have this moment and vertical load. So the left side due to the vertical load is going to be compression, and the left side due to the moment is going to be tension. So if numerically this F sub P is going to be larger than F sub M, so someone's going to say, give me an example. So I'm going to say if F sub P equals, let's say 6 KSF, all right, it's going to be F sub P. Just throwing here some numbers. And F sub M, I'm going to say this F sub M is going to be equal to what? I'm going to say maybe 3 KSF. If this can be 3 KSF, it's going to be compression 3 KSF here and compression 3 KSF. On the other side is going to be now tension 3 KSF. Now let me do the analysis on the left side of the footing. I have from the vertical load compression of 6 KSF. And then this side, also the left side, I have 3 KSF of tension. So we're going to say compression 6 minus 3 for the tension can end up with, we're going to say here, let me show it in this footing. I can show it in either one of these two. We're going to say 6 minus 3 is going to be equal to 3 KSF, and it's going to be compression. It's going to be the left side. Okay, makes sense? Yeah. How about the right side? I'm going to say the right side here is going to be compression of 6 plus 3 KSF as also compression is going to be 9 KSF. This is going to be the right side. So now the left side is going to be 3 KSF and the right side is going to be 9 KSF because the amount of compression here prevails. So you're going to end up with compression both sides. Yes, say like this diagram, like in here. So how come this happened? So I'm going to say again, this happened because the component coming from F sub P is just larger in value than the compression coming and tension coming from M over S. And with that, I ended up with trapezoidal distribution. So it's going to look like this. This here is going to be 9, and here is going to be 3, and this is going to be the stress distribution below the footing. Now imagine that I can repeat the same problem here. This is going to be different example, separate example. I'm going to say, what happened if the pressure here numerically is less than the pressure here? You can say, well, in the right side, there's going to be compression here, compression there, I can add it up. But the problem, this numerical value on the right side, in the left side, which means the tension side, is going to be higher than that of the vertical load. So you're going to end up by lifting the footing. And this exactly is going to happen in case B. So look at this. In case A, F sub P is going to be more than F sub M. And the soil pressure is going to be all trapezoidal. And this equation is good to analyze this problem. So when you have pressure here on both sides, you're going to say it's going to be F sub P plus or minus F sub M. Why plus or minus? Because at one time it's going to be additive, it's going to be all compression. The other time you're going to have subtractive, it's going to be negative, which means that you have tension on one side. So, okay. How about if I ended up by having some tension and the footing is going to start to lift up? Let's say in a case like this, it's going to be case B. And in this case, you end up by the stress distribution like this. So what's going on? I'm going to say in this case, this section of the footing was exposed to tension. And the soil cannot take any tension. Just imagine that you're talking here about sand or clay or whatever, right? Can you apply any tension to sandy soil? I'm guessing no. The sand doesn't have any resistance to that. But the sand is going to be good if you put pressure on it. It's going to be able to take this pressure of compression. But you cannot really apply any tension to it. So actually, the footing here is going to be lifting up from the soil. This is why you see here, this section of the footing, it has no stresses below it. And one side, you're going to have lots of compression. And you end up with the stress distribution like this. So you understand that here, when I have moment and axial load, I can say moment M equals to P times E, which means it's interesting. So I'm going to say M equals, I can say that M equals P times E. Understand that? And how much is this X? I'm going to say X equals 1/2 of the footing length, subtracting X, subtracting E. So X equals L over 2 minus E. Yeah, I have it in this equation here. So I guess if I give you here the moment and I give you P, you can figure out E. So we're going to say E equals M divided by P, right? And after that, you can figure out X. X is going to be this distance here. Distance from the point load to the end of the footing. Now, the stress that you have here, I can just give it to you by this equation. It says F1 equal 2/3 P divided by X divided by B. What is B? I'm going to see the dimension in the other direction. You know, this footing has a dimension perpendicular to the screen, right? So this dimension here is going to be called B. So I'm going to say this is here B. If this square footing is going to be B equals to L. So, okay, good. And I have here all definition for all variables. So there's two ways here to solve for this problem, for the soil pressure when you have a vertical load and moment. Number one, you need in your analysis to figure out F sub P is going to be P over A. Number two, you do F sub M, M over S. Compare the two values numerically. If In case A, F sub P numerically is going to be more than the stress coming from the moment. It means that you end up with trapezoidal distribution. And this equation should be fine, equation number 4. But if F sub M is going to be greater than F sub P, is going to be case 2. See this? F sub M is going to be greater than FP. And in this case, you need to use this equation here. This is going to be the stress below the footing on the soil. All right? We're good? All right. Now, I want to show you the reinforcing design for the footing. So let me go back here. I'm going to say now I have a footing that I need to design the reinforcing for. How can I do this? Now, let me go back here to this slide. I'm going to be talking here about 2 demands, which is right here. I have something called here service demand and ultimate demand. I use here the service demand to do what? To design the foundation size only, meaning length by width. So in your case, you need to find out dead load, you add it to life load, divide by the soil bearing pressure, 3000 PSF, which is 3 KSF, come up with the footing size. It's going to be square footing in your case. What you need to do after this, you need to design the reinforcing. So the question is, where did you get the reinforcing from? We're going to say, which load would you use to do the reinforcing? We're going to say, look at this. It says ultimate demand design of concrete members and reinforcing. So when you do the footing design for the reinforcing, this is going to be the force that you need to use. It's going to be the factor. You need to do the factor, which you have used for the column design. Are we good? Any questions? Since I want you to continue and do your design for the project, I'd like to go here to this example 8. So I don't want to continue. Look at this slide, number 41. So what did I jump? I skipped this analysis because I want you to finish your project, right? So I'm going to be ignoring this moment thing on footing, right? So I started here. I took it from, let's say, this example, example 1, slide 20. I jump it here to slide 41. What did I do this? Because I'd like to finish a complete footing design with gravity loads on. And the only reason I'm doing this, because you have the spring break. Otherwise, I would have continued and finished all the soil design for different footings. And then after that, we work on foundation design, which means reinforcing. So in this case here, what I'm doing, I will have to do it this way so that you can finish your design in the project. So in this case here, in this example, it says gravity reinforcing concrete footing 8.6 by 8.6 by 2 feet 6. Supports, the column size is 24 by 24. This is here the column size. The concrete strength, 3000 PSI. Column ultimate axial load is 680 kips. Now I'm going to put a box around this. I'm going to say, here you're talking about the ultimate load. Is this P service or P ultimate? I'm going to say this is here P ultimate, right? It's going to be P ultimate. And this P ultimate is the load that you use in concrete design, right? This P ultimate is the load that you use in concrete design. Not to size the footing. So someone's going to say, but how much is the surface load? I'm going to say, you don't worry about it because this footing size is already given to you. So you don't really need the surface load. What you need to do is just take P ultimate from here and continue to design your footing for the reinforcing, right? I said, great. And then it says here, the reinforcing is going to be most likely, it's going to be one of these four. So, okay, now I understand. Now let me see how to design the footing reinforcing, which is going to be very critical at this point to be able to finish your submitter. So I'm going to say, let me find here the stress right below the footing, the pressure. You say here, I have P dead load, and this P dead load, this is here a plan view, like top view, looking at the footing. This is going to be here the footing, 8.5 feet by 8.5 feet. And the column is going to be right in the center, 24 by 24 is going to be right in the middle. It's going to be 2 feet by 2 feet. I'm going to say here, the pressure, the ultimate pressure below the footing is going to be equal to the 600 kip, which means this 100 kips here is the ultimate load, divided by 8.5 squared. This is not going to be service level. And I don't need to compare this with the allowable soil pressure value, because this is already at the ultimate level. This is not at the service level. We're going to say it's going to be equal to 9.41 kip per square foot. This is going to be the actual ultimate pressure below the footing. Now, depth of the footing here, how did I get this? It says here 30 inches minus 3 minus 1. I'm going to say depth 30 inches was given. This is going to be the total thickness of the footing. I'm going to subtract here 3 inches for the clear cover and 1 inch, let's say, for the reinforcing bars. So someone could have said here, why 1 inch? You just subtract only half an inch. I'm going to say, fine, yes, you can do this. But don't forget that I have reinforcing in both directions. And an average depth for both directions is going to be 26 inches. So if you do it here, 26.5 is correct. If you do 26, you're also correct. Nothing's wrong with that. Now, if you remember that we had a picture for a footing, and let's say here's the footing, the elevation of the footing, and here's a column, right? 24 by 24 inch column. And the pressure is going to come from the bottom, and it wants to lift this cantilever up from both sides. So critical section for a moment is going to be right here at the face of the footing, at the face of the column. You see here? So I guess I should be able to move this here. So I'm going to move him just to the side. I'm going to say my critical section here for a moment is going to be right at the face of the column, meaning it's going to be right here. Because this cantilever wants to lift up, and the maximum tension is going to be here. So now I understand the reason that I have this to be hatched this way or shaded this way, because I know that this is going to be the critical section of moment on the footing.
Professor, I have a question.
Yes.
Is that how it is all the time? Like that's always where the critical face is?
Yes, it's going to be at the face of the column, right?
Okay, thank you.
No problem. But for shear, it's going to be different. You remember for shear, it was at the distance away from face of support, if you recall this issue.
Yeah.
So shear is different. For shear, critical section is going to be about here, let's say, roughly, something like that. For flexion, it's going to be right at face of column. All right. Critical section, I need to find out this, the cantilever length, this X. So you can say, well, this here, 8.5, subtract 2 feet, which is right in the middle, is going to be 6.5 feet, divided by 2. It's going to be 3.25. You see here, I can do it just quick, but if you want it to be written, you can play it. You can play with it this way. You see here, total of 8.5. You subtract 2 feet in the middle, you end up with 6.5. You have a right cantilever and a left cantilever. So you divide by 2 because they're equal to each other. So it is very common that when you have a square footing, you're going to have the column right in the center of it, right? You need to put the column right in the middle. Now I need to figure out how much moment do I have at this section. So I'm going to say the moment equals to the point load, the force that's pushing this up. So this force here is going to be perpendicular to this page, right? And it's going to be right here, perpendicular to the screen in this case. It's going to be going up like to your face. So it's going to be like this. It wants to push this up as a point load. This point load is going to be equal to this ultimate pressure multiplied by this shaded area. You remember when you do integration for the stress, means that you take the stress, multiply by this area. So if you are able to find out this area, the shaded area, which is x, now 3¼ multiply by 8½ and then multiply by the moment arm. And what is the moment arm in this case? I'm going to say moment arm is going to be distance from here to there, right? It's going to be the force, the point load. So we're going to say here, the pressure is going to be 9¼ I said, okay, times B. Look at this, Q ultimate times B. What is B? This is going to be B, the 8½ feet. So I'm going to say this is here B, right? This is going to be the width B. So you take the pressure, 9¼ times B times X. Why times X? To get you the area. So 8½ times X, 3¼ times 9.41 is going to give you the force. This moment arm is going to be X over 2, 1/2 of X. So I'm going to be taking this again, X, this is why I have X squared, and then divide by 2 at the end. Are we clear about this moment? How the moment was determined? Questions on the moment? Let me repeat it. So there's no questions means not there yet. I'm gonna say you have a force here. I'm gonna say yes. How much is this force? I'm gonna say this force is gonna be pushing upward. It's gonna be equal to Q ultimate, which is what? I'm gonna say Q ultimate, the 9.41, multiplied by this contact area, which is a shaded area, multiplied by B, which is this length, multiplied by X. So let me write it this way. It's going to be Q ultimate times B times X. Let me find how much is this numerically. I say Q ultimate is 941 times B, 8½ feet, times X is going to be 3½ feet. Can someone help me and tell me how much is this in kips?
Looks like 279.9 or 280.
Okay, yeah, 280 is good. So this is going to be the force. Now, this force is going to be acting right here. You have here 279.9. Now, the distance from this point load to the critical section is how much? Yes, say this distance here, 3¼ Therefore, this distance from here to there, this moment arm, I can put a solution to them. I'm going to say this is going to be equal to 3¼ divided by 2. 1.75 feet, right? Okay. Now, how much is the moment in this case? I'm going to say the moment at this face, and say here we go. Now, M at this face of support is going to be equal to F times 1.75, the moment arm. It says times R equals 279.9 times 1.75. Can someone help for the moment value?
489.9.
489?
Yeah, 0.9.
So how come? Can you try this math, please? The math from here?
Oh, maybe I did something wrong.
No, I'll tell you what's wrong. This is my mistake. This is not 3½. This is 3¼ right? Make sense? This length here, X is a 3/4, not 3½.
Yeah, makes sense.
Okay. Now, can you give me the new number?
It looks like 259.95.
All right. Good. And here, I'm going to say here 259.9 times 1.75 has to be 422.4, right? You're good? So now I have the ultimate moment on the footing. The question is, how much is the depth? You can say here's the depth, 26 inch. How much is the width of this section? You can say this section actually, if you cut a section like this, the width B for the section is going to be 8½ feet. Now put it in inches. So okay, This is gonna be a lot. I'm gonna say 8.5 times 12 is how much is this? I'm gonna say 102 inches. So now I have a rectangular section, because when you cut the section, you cut it this way, and the reinforcement is gonna be running in the X direction, right? So I said, let me try here 10 number 7, right? I'm gonna start right here, look. And please, I want you to look at this. You pick one of the answers, and then you say, I'm gonna start with this reinforcing, 10 number 7. Meaning what? AS provided this is gonna be 10 times 0.6, is gonna be 6 square inches. Now I can solve my equation here. You remember A for rectangular section, no compression reinforcing, non-T section is gonna be A equals AS times Fy divided by 0.85 F prime C times B. Look at the B value here. It's gonna be this 8.5 feet. So I can write here, this gonna be B is gonna be 8.5 feet, right? Which means 102 inches. The entire width of the footing. Meaning your footing is gonna be like this. And this width is gonna be 8.5. When I take this section, I say this is here 8.5 feet. How about the reinforcing? I'm gonna say the reinforcing is gonna be right here. The 10 number 7 is gonna be like this. We're gonna have here 10 bars. In beams, I used to have 4 or 5 bars, right? Now all of a sudden the footing is gonna be the entire width of the footing, right? You're gonna have here lots of rebars, which is this 10 number 7. And it's gonna be a rectangular section. And we're gonna have the same thing. We're gonna have the neutral axis, we're gonna have A and C and the whole thing here, right? Now look at A. A is gonna be 1.38 inches. I guess now you know how to do Phi for rectangular section. And you need to be sure that this Phi is gonna be greater than M sub U, M ultimate. So for 10 number 7, right, I'm gonna run my equation. I don't think I need to show you here how to find out the Phi factor. Now this becomes something in the basics, right? You know how to do this. How to find out Phi factor, how to find Phi min. So your Phi min becomes 683. Your demand is how much? 422.4. Based on what? Based on the ultimate load. Based on this. This ultimate load, right? Your moment here equals 422.4. Your capacity, if you're gonna go here with 10 number 7, is 683. Now with that, I designed a complete footing. You have a very good example, right? It shows you here in this example how to size the footing. That was the first example, example 1. And example number 8, it shows you how to design the reinforcing. Some items here that I'd like to stress on. Item number 1. When you do the footing size, you do it based on the service load, meaning just dead load plus life load. Just to come up with the footing size, this is gonna be soil design. We call this soil design actually. Item number 2, when you do the reinforcing or the shear or whatever, if you are designing the concrete member, you need to use P ultimate. P ultimate means 1.2 plus 1.6 or 1.4. I mean, the standard load combination that you have used in the past, like in here. I'm gonna bring it to here, right? It's gonna be P ultimate. So for the footing size, you design the soil, it's gonna be service, just dead load plus life load. For reinforcing, you're gonna be using load factors. Okay. For reinforcing design, you need to find out the ultimate soil pressure. This soil pressure not to be compared with the allowable soil pressure. Why? Because it's gonna be much larger. This ultimate soil pressure includes some load factors. So you cannot really compare it with the allowable soil pressure. Again, this ultimate soil pressure is not to be compared with any other soil pressure. This just used. The reason this type of stress is here, we just use it to design the reinforcing. This is not to size the footing. To size the footing, you're talking here about P service. Like in this example, look at this. It's gonna be P service demand, dead load plus life load. That's it. So if you're sizing the footing here, comparing soil allowable soil bearing pressure like the 7 KSF with the actual soil pressure, or come up with the size, use service load. If you want to design for the reinforcing, you need to use the ultimate load, 1.4 versus 1.2 dead plus 1.6 live. And now you can design the reinforcing. Any questions on this submitter before I let you go? All right, go ahead, please. Sign out. Type your name, please. And enjoy your break.
Bye, Professor. Thank you.
Thank you. Have a good break.
Thank you, you too, guys.